Hello and welcome to Algebra 2 Lesson 60. In this video, we're going to learn about solving equations with radicals. So when we start talking about solving an equation with a radical involved, we need to think about a new rule. So if both sides of an equation are raised to the same power, so just as an example, let's say I have squared both sides of an equation. All solutions of the original equation, meaning before I squared both sides, are solutions to the new equation. But the catch to this is going to be that it doesn't go in reverse. Each solution to the new equation, in other words, once I've squared everything, if I solve that new equation, it's not necessarily going to work in the original. Okay, so we have to check for something known as extraneous solutions. And these solutions do not work in our original equation. So for you to understand this, I wrote a little simple example here. And this is very common in any textbook you're looking at. You'll see something like x equals 3. And right now we know that if we replace x with anything other than 3, we would get a false statement. All right, I can only say that 3 can be replaced for x, so I get 3 equals 3. All right, so now that we understand that, if we squared both sides of the equation, let's just say this became x squared, and if I square 3, I would get 9. What happens here? Well, 3 is still a solution. If I plug in 3 there, 3 squared equals 9. That's true. 9 equals 9. So it seems like there's no problems. Everything is good to go. But remember, if I square a negative, it becomes a positive. So this is where kind of information is lost, okay? We've squared both sides, and we've lost the information on whether or not it was a positive or a negative. So in other words, what I could also have as a solution here is negative 3. So if I plugged in a negative 3 there, and I squared it, right, the negative and the 3 would be squared, this would also be equal to positive 9. So you'd get a true statement, 9 equals 9. So with the equation x squared equals 9, there's two solutions. Your solution set would contain negative 3 and positive 3. But again, with the original, there's only one solution. X here can just be 3. So if you've squared both sides to get to this, and you end up with these two solutions, you've got to plug them back in to the original equation, and you've got to figure out if they work or they don't work. You plug in a 3, you see that it works, you know that's a valid solution. You plug in a negative 3, you'd see that negative 3 does not equal 3. So negative 3 is an extraneous solution. It's something you have to reject. All right, so let's look at the procedure to solve an equation with radicals. Basically, all you want to do is isolate one of the radicals first. For your easier problems, the one you get introduced to, you basically just have one radical, and normally it's just a square root. So with those, you just push the radical on one side, you push your number or whatever else on the other side, and then you're going to raise both sides of the equation to a power equal to the index of the radical. So in other words, if it's a square root, the index is a 2, so you square both sides. If it's a cube root, the index is a 3, so you cube both sides. So on and so forth. Now, with your harder problems, the ones you're going to see at the end of the section, or let's say you're doing a college algebra course, or even in this Algebra 2 course, you're going to get problems where there's more than one radical in there. So you might have to go back and isolate the radical again. So we put here, repeat the previous two steps if necessary. Sometimes you got to do it on a tougher problem. Sometimes you don't if you get something simple. Then you're just going to solve the equation and check all solutions in the original equation. Again, you've got to check all solutions in the original equation. Okay? It's very, very important that you do that. Because if you don't, again, you might end up reporting some answer that works in your transformed equation, okay, your new equation, but it doesn't work in the original, right? Your extraneous solutions. All right, so let's start out with something very, very easy. We have that the square root of p plus 4 is equal to 5. Now, we're going to do this kind of as it sits now, and then I'm going to show you kind of with exponents so that you understand both ways. So I can, again, square both sides of this equation. And what happens here? The squaring undoes the square root. So you can basically cancel those out. And then what's left under the radical symbol, your radicand, is what's going to be there. So you'd have p plus 4 is equal to, if I square 5, we know we get 25. Very, very easy equation to solve. If we subtract 4 away from each side of the equation, we'd find that P is equal to 21. Now, let me just erase this real quick. Let's think about the original equation we were presented with. If we plugged in a 21 there, what do we have? A true statement. 21 plus 4 is 25. The square root of 25, or at least the principal square root of 25, is in fact equal to 5. So you would get 5 is equal to 5. So this checks out. Right? You can say your solution set contains just the element 21. Now, let me show you this using exponents. And a lot of students will see this and like, oh yeah, I get it now. Okay, this is a good way to kind of think about these. If we know already that taking the square root of something is like raising it to the power of 1/2, what we can do is we could say that we have P plus 4, and inside of parentheses, this whole thing is raised to the power of 1/2, and this equals 5. Now, using what we know about exponents, again, if we square both sides here, let me just put this inside of brackets, and we're going to square this, and we're going to square this. What happens here? Well, we're using our power to power rule. If you're raising a power to another power, you multiply the exponents. So what is 1/2 times 2? Well, that's 1, right? These are going to cancel, and it's going to be basically raised to the first power. So in other words, this would cancel with this, and I'm just left with P plus 4. So I have P plus 4 is equal to 25. And again, we solve that, and we get that P is equal to 21. So just another way to kind of think about it, if you see this on a test and you're drawing a blank on what to do, you can convert your square root into raising it to the power of 1/2, and then it's obvious. Okay, what do I need? Well, I need to square it, because squaring something that's raised to the power of 1/2 would get me to an exponent of 1. All right, for the next one, we're going to look at the square root of 3x minus 16 is equal to the square root of 19 minus 2x. So in this case, we have a square root on one side and a square root on the other. You just square both sides. So I'm going to square this side, and I'm going to square this side. And what's going to happen? Well, again, this would cancel with this would cancel with this, and we're left with the radicand in each case. So you basically just have 3x minus 16 is equal to 19 minus 2x. Now, we know how to solve something like this. Very, very simple. We can add 2x to each side of the equation, and we can add 16 to both sides of the equation. So this is going to cancel over here, and this is going to cancel over here. 3x plus 2x is 5x, and this is equal to 19 plus 16 is going to give us 35. We divide both sides of the equation by 5. We get that x is equal to 7. Again, we want to check to make sure that this is a valid solution. So let's erase all this. And we're going to plug in a 7 for x here and here. And let's see if we get the left side equal to the right. So we would have the square root of 3 times 7 is 21. 21 minus 16 is 5. And this is equal to 19 minus 2 times x. 2 times 7 is 14. 19 minus 14 is 5. So you get the square root of 5 over here as well. Now the square root of 5 is an irrational number, but you have the square root of 5 equals the square root of 5. Same thing on the left and the right. So we have a true statement here. So our solution set for this equation just contains the element 7. All right, let's take a look at a harder type problem. So now we have 8 plus the square root of 34 minus 3b is equal to b. What you want to do is you want to isolate your radical on one side. So I want to move 8 over here. So let me just subtract 8 away from each side of the equation. And what's going to happen is you'd have the square root of 34 minus 3b. And this is equal to b minus 8. Now I've isolated my radical. So all I need to do now is just square both sides. That's going to get rid of that radical. So we'll square this side as well. This will cancel with this. And I just have my radicand. So I just have 34 minus 3b. And this is equal to. Now, don't make this mistake. We talked about this when we talked about polynomials. I see this all the time. You learn in polynomials and then you forget it. You go back and you say, well, this is b squared minus 8 squared. It is not. You have to expand this, right? Using FOIL or using your special products formula. This is b minus 8 times b minus 8. Okay, it is not b squared minus 8 squared or b squared minus 64. That is wrong, okay? So we know the formula for this. This is b squared minus 2 times b times 8, which is 16b, then plus this last guy 8 squared, which is 64. And again, this is from our special products formulas. Those are the things that, again, we talked about this because you learn that and then you get a problem like this later on and you're just like, boom, I got it. Okay, you don't have to sit there and do FOIL every time. So now that we have that, let's say this is equal to 34 minus 3b. Let us add 3b to both sides of the equation. So that's gone. And let's also subtract 34 away from each side of the equation. So that's gone. So I'm going to rewrite this. This would be 0 over here because everything's canceled. But I'm going to move all this to the left. So we would have b squared. Negative 16b plus 3b is going to give us negative 13b. And then 64 minus 34 is 30. So plus 30. And of course, this equals 0. And again, all I did was I just moved this to the left and I moved that to the right. Now, we have a quadratic equation. We have in Algebra 2 so far only talked about how to solve this equation if it's factorable. So we only give you examples here where it's factorable, but again, in a few lessons, we're going to start talking about the square root property, the quadratic formula, completing the square, things we learned back in Algebra 1 at the end. So most of you can just do this with the quadratic formula. If you want to do that, that's fine. At this point, we're still doing it with factoring. So if I factor this guy, I'd have a b here and a b here. Two integers whose sum is negative 13 and whose product is 30. Well, that's going to be negative 10 and negative 3. So we solve this using, again, our zero product property, or you could say your zero factor property. And all you're doing is you're taking each factor, this b minus 10, that's a factor, and this b minus 3, that's a factor, and you're setting them equal to 0, and you're solving. So it's b minus 10 is equal to 0, or it could be true that b minus 3 is equal to 0. Either one would work as a solution. So let's add 10 to each side of the equation. We'll get b is equal to 10. Then or, let's add 3 to each side of the equation. We'll get b is equal to 3. Now, these are the solutions for, again, our transformed equation. They're not necessarily going to work in the original. So the solution set here is 3, 10. But let's go back up to the top and let's see if these work out. All right, so let's go ahead and check these. So if I had a 3 plugged in for b, you would get 8 plus the square root of 34 minus 3 times 3 is 9 is equal to 3. 34 minus 9 is going to give you 25. So the principal square root of 25 is 5. So you'd have 8 plus 5, which is 13, is equal to 3. Well, that's not true. 13 doesn't equal 3. So we've got to reject that. We're going to reject it. It's an extraneous solution. Okay? It works in the transformed equation, but it does not solve or satisfy the original. Now, let's try 10. So if we plugged in 10 here and here, what would we get? We'd have 8 plus the square root of 34 minus 3 times 10 is 30 is equal to 10. 34 minus 30 is 4. So you'd have 8 plus the square root of 4 equals 10. You can all see at this point that this is going to work. Square root of 4 is 2. So you'd have 8 plus 2 equals 10. And of course, this leads to 10 equals 10. So this one does work as a solution. So the solution set for this equation is going to contain one element, just the element 10. Okay, so you could say b is equal to 10. All right, let's take a look at another one. We're going to try one that's a little bit harder, or not harder, but just more tedious. So I've got one radical that's isolated on one side. On the other side, I've got a radical plus a number. So what we want to do is, again, just square both sides. And you're not going to be radical free the first time you do this here. So if I square this side, this will cancel with this, and we'll have the radicand, which is 9k minus 2. Then this is equal to, over here, I'm going to go ahead and use my special products formula. You have to be just very careful about this. This right here, you're going to treat it just like you would, let's say this is x and this is y. Okay, you'll see what I mean. So for that formula, the first guy gets squared. So it's 4 squared plus 2 times the first guy times the second guy. 2 times 4 is 8 times the second guy, which is the square root of 4 minus k. Then plus, you've got the last guy squared. So if I squared the square root of 4 minus k, I'd be left with 4 minus k. All right, so now that we have that, we want to do some simplifying. The easiest thing is 4 squared, we know that's 16. Let's go ahead and just write that. And then 16 plus 4 is 20. So we could say that we have 9k minus 2 is equal to, again, 16 plus 4 is 20, plus 8 times the square root of 4 minus k, and then minus k. Now, we know that we could add k to both sides of the equation, and that will cancel. We know that we can subtract 20 away from each side of the equation, so that will cancel. And so what we'll have is what? We'll have 10k minus 22 is equal to 8 times the square root of 4 minus k. Now, I have just a radical times a number on one side. Is everything divisible by 8 here? Because if I divide it by 8, I can get rid of that out in front. But 10 is not divisible by 8, and 22 is not divisible by 8, so I wouldn't do that here. Okay, you can do it, but I think it would cause more work because you're going to end up with some kind of nasty fractions to work with. So let's go ahead and just square both sides of the equation. And what are we going to get? Over here, we're going to use our special products formula. We know we would square 10k, so that's 100k squared. Then minus 2 times this times this. 2 times 10 is 20. 20 times 22 is 440. And then, of course, times k. Then the last guy is plus this guy squared. 22 squared is 484. Then this is equal to, remember, this is multiplication here. So it's kind of like you're saying you have 8 squared multiplied by the square root of 4 minus k squared. You just got to make sure that you raise both of these to the power of 2. So in other words, you can kind of put this inside of parentheses and say 8, again, will be squared. And then this guy inside of parentheses, the square root of 4 minus k, that's raised to the power of 2 as well. All right, so let's continue simplifying. We've got 100k squared minus 440k plus 484 is equal to 8 squared, of course, is 64. And then the square root of 4 minus k squared, again, this cancels with this. So you can have this is multiplied by 4 minus k. And this has to be in parentheses because, again, this guy right here, this 8 squared, is multiplying this whole thing. Okay, so don't make the mistake of just saying, oh, we've got 64 times 4. That's not going to work. Okay, you've got to multiply it by the 4 and by the negative k. All right, so let's continue here. So we've got 64 times 4, which is 256, and then minus 64 times k, which is just 64k. So over here, we still have our 100k squared minus 440k plus 484. All right, so let's add 64k to each side of the equation. That'll cancel. Let's subtract 256 from each side of the equation. That'll cancel. So we'll end up with 100k squared. And then negative 440k plus 64k is negative 376k. And then 484 minus 256 would be plus 228. And this equals 0. Now again, so far in Algebra 1, we've only talked about kind of doing these problems, these quadratic equations with factoring. The first thing you would notice is that everything is divisible by 2. 100 is divisible by 2, so is negative 376, so is 228. Now, the other thing is that everything is divisible by 4. So a cool little trick to work with smaller numbers, we can divide both sides of this equation by 4. If I divide 0 by 4, I just get 0. So what does that matter, right? So this will still be 0. If I take 100 and divide by 4, I get 25. So this would be 25k squared. Then minus 376 divided by 4 is 94. So this would be minus 94k. And then plus 228 divided by 4 is 57. So now we have 25k squared minus 94k plus 57 equals 0. All right, so with a quadratic equation, again, you can use the quadratic form if you want. We haven't gotten to that yet, so we're going to solve this by factoring here. So I want two integers whose sum is negative 94. and whose product is 25 times 57, which is 1,425. So if you factor this, again, we know this came from 25 times 57. This is 5 times 5. This is 19 times 3. So right away, you know that you want two negatives, right? Two negatives sum to a negative, two negatives multiply to be a positive. So thinking about that, 5 times 5 times 3 is 75. It's 25 times 3, that's 75. 75 plus 19 is 94. Just got to work out the signs, right? You just want all that to be negative. So what you would want is two integers, negative 75 and negative 19. So we're going to use those two to rewrite that middle term. Okay, so we'll have 25k squared minus 75k minus 19k plus 57 equals 0. From the first group here, we can pull out a 25k. So we'll pull that out. So inside, we'll be left with k minus 3. From the second group here, because the signs are in a different order, right? This is plus, this is minus, this is minus, this is plus. We're going to pull out a negative 19, and that'll leave us with k minus 3 inside. And so we have this common binomial factor, this k minus 3. That can be factored out. So let's go ahead and take that out. And what we're going to have is, we'll have k minus 3. Again, we're factoring that out. Times, what's left is going to be 25k minus 19, and this equals 0. Again, zero factor property. So you've got k minus 3 equals 0. Add 3 to each side. You get k equals 3. Or 25k minus 19 equals 0. Add 19 to each side of the equation. You'll get 25k is equal to 19. Divide both sides by 25. And you'll get that k is equal to 19/25. We need to check both of these in the original equation. So k equals 3 or k equals 19/25. All right, so let's check again. You want to check k equals 3 or k equals 19/25. All right, let's do 3 first. That one's easier to do. So if you plug in a 3 here and here, you would have the square root of 9 times 3, which is 27. Let me just go ahead and write that. 27 minus 2, which is 25. So the square root of 25 is equal to 4 plus the square root of 4 minus 3 is 1. So it's the square root of 1. Square root of 25 is 5 equals 4 plus square root of 1 is 1. So 4 plus 1 is 5. 5 equals 5. So yeah, this one's going to check out. Now the other guy over there, that's going to be much more tedious. But again, on these, you have to check them. So it's not something you can just kind of skip through. So we'd have the square root of 9 multiplied by 19/25 minus 2. This should be equal to 4 plus the square root of 4 minus 19/25. All right, so over here, 9 times 19 is 171. So this would be the square root of 171 over 25, then minus 2. Now I want a common denominator going, so I'm just going to multiply this by 25 over 25. So you might as well just say this is 50 over 25. So if I did this operation, 171 minus 50 would be what? That would be 121. So this would be the square root of 121 over 25. And then we know the square root of 121 is 11. We know the square root of 25 is 5. So you might as well just write this is 11/5. So this is equal to, you've got 4 plus the square root of, for 4 minus 19 over 25, again, if I get a common denominator going, multiply this by 25 over 25, it's essentially 100 minus 19, which is 81. So this would be the square root of 81 over 25. We know the square root of 81 is 9. We know the square root of 25 is 5. So this should be equal to 4 plus 9/5. So get a common denominator going here. Let's multiply this by 5 over 5. You'll get 11/5 is equal to, 4 times 5 is 20. So you'd end up with 20 plus 9, which is 29 over 5. So 11/5 does not equal 29/5. That's false. So we have to reject that solution. So let's go back up and let's reject this guy because it doesn't work in the original equation. So your only solution here is going to be that k is equal to 3. Or again, using a solution set notation, you just put 3 as your only element. And so again, that's why it's so important to check these. And I know you get some of these that are going to be really, really tedious, but they throw those in there just so you get some good practice. All right, let's take a look at one that's a cube root now. So we have the cube root of 31 minus x is equal to the cube root of x squared plus 11. So with this one, it's very easy. Again, if I have a cube root, I want to raise everything to the third power, or I want to cube it. So what happens is this cancels with this, right? You can think about this as I have the 1/3 power raised to the third power. 1/3 times 3 is 1, right? So they just cancel each other out. I'm left with just my radicand, which is 31 minus x. Over here, same thing. This cancels with this. I'm left with my radicand, which is x squared plus 11. And so all we really need to do here, let's add x to each side. And let's subtract 31 away from each side. That'll cancel, become 0. You will have that 0 is equal to x squared plus x. 11 minus 31 is going to give us negative 20. And we could rewrite this as x squared plus x minus 20 is equal to 0. Now again, we're going to solve this using our 0 factor property. So let's factor this guy and see what we can get. I know this is x and this is x. Two integers whose sum is 1 and whose product is negative 20 would be positive 5 and negative 4. Now we'll set each factor equal to 0. So you'll have x plus 5 equals 0, or x minus 4 is equal to 0. If we then subtract 5 away from each side of the equation, we'll get x is equal to negative 5. Over here, if we add 4 to each side of the equation, we'll get that x is equal to 4. So these are the two proposed solutions. All right, so the two solutions we found were x equals negative 5, and then x equals positive 4. So you're just going to plug them in like we have been. So if I plug in a 4 there and there, what will we get? We'll have the cube root of 31 minus 4, which is 27, is equal to the cube root of 4 squared, which is 16, plus 11, which is 27. So obviously the cube root of 27 does equal the cube root of 27. This is basically 3 equals 3. So this guy's going to check out. The next one we want to try is negative 5. Okay, negative 5. So let's plug that in there and then there. So 31 minus a negative 5 is like 31 plus 5. 31 plus 5 is 36. So you'd have the cube root of 36. Then over here, you have to be careful because you have negative 5 squared. Negative 5 squared is 25. 25 plus 11 is 36 as well. So we'd have the cube root of 36 equals the cube root of 36. Same value on each side, so this solution works as well. So your solution set for this equation contains two elements. We have negative 5 and 4.